Okay. So there is such a thing as Bernoulli's formula, if you have heard of that. The question I had, though, is basically, how many Bernoullis do you know about? Because usually we tend to think, okay, that's this person's stuff. This is Gauss's formula. This is Euler's formula. This is whatever. So Bernoulli has a formula, and I used to think there was one, maybe two of these guys. But it turns out that in about less than 100-year period, there are no less than 8 mathematicians who are named Bernoulli, and they're all related. So the two main ones we're going to talk about today are brothers, but there's also uncles and nephews and cousins and all kinds of stuff. And so, like if you're reading through your book or if you see different ones, even we have this thing in the hallway that's about the history of mathematics, and they talk about Bernoullis. You can see there's different Bernoullis in there, and different ones did different stuff. So the two that we're talking about today, primarily, we'll kind of mention at least one of the other ones, but these are James and John, okay? And James is the older brother. Let me find his date. To the right page. Oops, sorry. What is it? So James is the older brother, and his dates are 1654 to 1705. So we're getting a lot more modern, you know, only within the last 400 or so years. And we start to see stuff like, oh, you know, America is going to be its own country soon, you know, and we're going to have our Declaration of Independence and stuff like that. So, again, all this stuff is happening long before we're even considered a legitimate country. So what happened here is that the Bernoulli family was actually from Antwerp, and they were Protestants. And there is a very Catholic-dominated Spain that basically attacks Antwerp and runs out the Protestants. And so they run for cover, basically. So these guys end up, the whole family, okay, they run away from Catholic persecution, so to speak, and they all end up in Basel, Switzerland. And it's actually like the people who are doing the running are basically the generation we're about to talk about's grandparents, okay? So 2 generations ahead. They end up in Switzerland. They go a couple of different places, but Switzerland tends to be more accepting of different lifestyles and things like that. So even back then we see that they're a little more neutral. So this is a good place for people who are being persecuted to go to. So they end up there. James is the older of the 2 brothers, and his dad wanted him to go and be a minister, so he wants him to study theology. So he starts with that, and then he says, no, you know, I just can't do it, basically. I don't want to be a theologian. I want to do math and astronomy. So he defies his father, which was kind of a big thing, and later on in life, I think he actually got a degree in theology, but then he goes, no, I don't want to do that. So later on in life, he adopts this weird motto. He seems to be, if you read some of his writings and stuff, he's a little bit arrogant, a little bit maybe self-centered. So his motto is a weird one. I study the stars against my father's will. Which is not really much of a motto to live by. Okay, but that's what he says. So he gets his degree in theology, and then he also studies math and astronomy. I don't know that it's deliberately to make his father mad, but for sure he kind of takes pleasure or whatever in the fact that he's being his own man and doing his own thing. Okay, so after he gets his degree in theology, he decides he's going to travel. So he goes to England, he goes to France, different locations. He just wants to see, and in particular while he's traveling, he's looking for people who are studying math. Okay, so he wants to expand on his knowledge in mathematics and things like that. So he actually ends up meeting with some of the fellows in the Royal Society while he's in England. Okay. We don't think that he, at this point, necessarily meets Leibniz, because Leibniz is actually like in Paris. But he does meet with Robert Hooke, and he's able to talk to different ones about some of the theories of light and things like that. And in particular, he becomes interested in calculus and the writings from Leibniz, the stuff from Newton and all of that. So we'll see that that's where his interest kind of lies. In 1682, he founds a school, and it's for math and science students. It's kind of an interesting thing to do because we don't necessarily, we have like universities and stuff like that, but not necessarily things that are just for math and science people. And in 1687, he becomes a professor of math. So much for being a monk, I guess. Professor of math. And he's at the University of Basel, which is where they're from, back in Switzerland. And he stays at that post in Basel until he dies in 1705. And he is the older brother, but he dies is seemingly young compared to his younger brother. When they're young and James starts studying math, he has this desire, I guess, to bring his brother along with him, John, and to have him study math also and to teach him. So he tutors him a lot, and they work together, and they seemingly get along really well, and all is lovely. But later on in life, that kind of turns into a bit of sibling rivalry because they're both investigating calculus at the same time and both trying to prove theories at the same time. And like I said, James is a little arrogant, so he'll be like, look at this wonderful thing I did, blah, blah, blah. You know, and I couldn't prove that, but it doesn't matter because it's not important. And then John will come up behind him and go, ha, I proved it. You know, that kind of thing. So it's a bit of a sibling rivalry going on with them. He is considered, James is considered one of the first people to truly understand, we'll call him one of the first mathematicians, fully understand Leibniz's work in calculus. The notations, all that he's done, the differential stuff, derivatives, and it's interesting because he tutors his brother John, and then his brother John ends up tutoring L'Hopital, which we've all probably heard of L'Hopital's rule, right? So it becomes a bit of a think tank almost, where all these mathematicians are sitting around tutoring each other and working with each other, and they start doing this, and Leibniz is in on this, writing back and forth, sending people things that they've learned about calculus and they've figured out, and then challenging the other ones. Oh, I'm thinking about this problem. Can you figure out how to work that? And things like that. But not in the manner of the Renaissance duels, so to speak, where they're like fighting it out about who's going to be the smartest mathematician. More in a collegial, let's work this together and see if we can come up with something kind of way. So seemingly, aside from some sibling rivalry, getting along well. So they have a group of mathematicians working on problems. In calculus. And it's said that almost all of modern calculus, plus a little diffie-q, let's say the beginnings of differential equations, was discovered by this group of people? By the late 1600s. Okay, so they have like a cohort, and they're all working on applications of calculus and things we can do with calculus. And it's not just the derivative that Newton envisioned way back when, right? And that Leibniz came up with that lovely notation. Now we're starting to talk about integral calculus. We're starting to talk about differential equations, differential calculus. Is there any way that we can do lots of applications? So really expanding to what you would probably study today in modern, and building on some notation as well. Okay, so this guy, he's the first one to know. He teaches John teaches L'Hopital. Remember that because it's going to come back to bite us later. They expand on Leibniz, and what they say is that the calculus, and it's interesting because they almost always call it the calculus, has tremendous analytic power while still being flexible. And of course, they don't know the extent of the calculus, the power of calculus. Like, I'm sure while they understand it's very powerful, they probably didn't envision wonderful things like electrical engineering and stuff like that we have today that's founded on that calculus idea. So I think that they probably couldn't necessarily foresee all of that. Okay. James wrote a book. It's called Ars Conjectandi. Okay, Conjectandi. Okay, which is the art of conjecture. Okay, and I'll talk to you a little bit about, there's like 4 major sections of this. But the interesting thing about it is he wrote on this book for over 20 years. And in fact, he never completed it. He died before it was done. When he was finished, he actually gave, and I don't understand this necessarily, except that we know that he had some rivalry with his brother. So he gave all of his work to his 17-year-old nephew, Nicholas. Okay, who actually does become a mathematician later. And he says, it's up to you, basically, to complete this and to publish it. And he was supposed to, I guess, smooth it out and make it nicer and all that kind of stuff. So he does that, and basically, Nicholas looks at it and is seemingly just overwhelmed by the amount of material that's in it. And he says, I can't do anything with this. And so after his uncle dies, I think it's like about 7 years, we'll say about 7 years after, we'll put a question mark that, somewhere in there, after James's death, Nicholas just takes it and publishes it, as is. Flaws, incomplete studies, whatever, he doesn't care, basically. And there's something about that I'm not really up to the task of making it better. Maybe he doesn't understand it fully, but he's trying to get it out there, just get it to the public, let people see it, and then other mathematicians can benefit from what his Uncle James has done. It was published in 1713 in Latin, which is probably the language that James wrote it in, would be my guess. Okay, so what about it? This book, The Art of Conjecture, it's 4 parts. Okay, so the first part is basically he takes any proofs that he already knows from different people's works, like there was those 2 brothers that were in Holland, the Huygens. who had done some work on probability and stuff like that. He takes all these works on probability and he extends them. Okay, he comes up with alternate proofs, and he clarifies areas that need clarifying that were blank. Okay, so he's doing a lot of that kind of stuff. That's the first section of it. Okay, section 2. He gives out basically like a huge table or something like that, all the results of combinations and permutations that are common. Okay, so basically if you need to find some kind of permutation, you're not sure. Remember that all of this probability theory mainly centered around games of chance and whether or not people were going to live, like mortality rates, population growth, stuff like that. So he's like, okay, here's all of these combinations and permutations that people might need. And while he's at it, he goes ahead and he talks about the binomial theorem, which we actually know they've had it for a while, right? I think Newton did some work on it. Pascal had his triangle that we talked about last week. He gives another form for Pascal's triangle and talks about that. But the cool thing that he does is he gives a proof of the binomial theorem. Okay. Yep. His proof, it's interesting, is only for positive integral powers. So later, a couple of other people will actually work on this binomial theorem and the proof for it. And, I can't remember who does the fraction one. I think it's maybe John does the fraction one. But a couple of different people will do fractions and what if these powers are negative and things like that. So it actually is kind of an interesting thing that people are really focused in on at this time. So he gives the original proof basically. His third section has 24 problems. Okay, and these are all problems that will deal with games of chance. So again, gambling, dice, cards. So 24 problems for the, interested mathematician to do on their own time whenever you have, some spare time. Work on these problems. And the last thing he does, he writes something and it's called, it's really long, I apologize, it's not my fault. Applications of the previous study of civil, moral, and economic, I told you it's long, problems. Okay. And I guess he just doesn't want to say more about gambling because that's what this is. So, applications of the previous study of civil, moral, and economic problems. Okay, so when you think about it, gambling is actually, and still is, one of those areas where some people would be for it, other people would be against it, so it might be divisive. You might have arguments in public about whether you should be throwing dice or not throwing dice and stuff like that. And of course there is an economic factor to it, right? We saw where the Mirror the other day made his entire life basically gambling. Okay, that's how he supported himself. So people did that, and so it is economic. So basically what he's saying here is, okay, people are gambling, but how can we apply that to mathematics and how can we improve on the study basically? So he does a couple of things. These are philosophical problems about probability theory. Sorry, too many P words. Philosophical problems about probability theory. Trying not to let my tongue get twisted on that. Probability theory. Okay, and what he does is he comes up with the very first limiting theory, like an actual theorem for probability. And so think about it. We're taking limiting theorems, so we're using calculus to talk about probability and whether or not something's going to happen. In your book, page 473, let me find it real fast, I'm sorry. He was proud of his result, the first limit theorem of probability, as is apparent from his own words. This is that problem which I am now about to impart to the public after having suppressed it for 20 years. So he's just kept it to himself. It is difficult and it is novel, but it is of such excellent use that it places a high value and dignity on every branch of this doctrine. So he's saying this is such wonderful mathematics that it's going to lift probability out of the realm of gambling only and life expectancy only, and it's going to give it legitimacy. Okay, so all of a sudden this is going to be a real branch of mathematics, according to him. So what exactly is he talking about? It becomes called Bernoulli's theorem. Okay, but you probably may not know it as that name because a later mathematician took it and boiled it down and called it the law of large numbers, which you probably had heard of that. Okay, and so it's a brand new, unique thing, and it's going to lead to lots of applications of probability theory in math and science. So what is this law of large numbers? Does anybody know it? What's it say? This is one of those things in the introductory statistics class that I teach, which is just for freshmen. They're not even math majors. They don't care anything about math. That they actually really kind of go, oh, okay, that makes sense. And it's one of those kind of pinnacle moments in that class that I like to show them, this law of large numbers. It comes straight out of probability theory. So, for instance, if I'm flipping a coin, and I ask you, what's the probability that I'm going to get heads on that coin when I flip it? 1/2, right? It's 1 out of 2, okay? And everybody knows that. Well, that's the theoretical probability, right? Okay, so we say, theoretically, when I flip this coin, what that means is that 1 time out of 2 that I flip it, I should get a head, right? Because there are 2 options, and so 1 out of those 2 is heads, okay? So theoretically, that's what happens. But what if I sit here and I flip it twice, and both times I get tails? Does that mean the theory's wrong? No. What if I flip it 10 times and 8 out of those 10 times I get tails? So I only got 2 out of 10 heads, which is 1 out of 5. Does that mean my theory's wrong? No. So what Bernoulli said was, he said, okay, we're going to take a limit. We're going to have a really small, it's basically epsilon. And we're going to not worry about, we're going to do this experiment basically lots and lots and lots and lots of times. That's the large numbers part. I'm going to flip that coin lots and lots and lots of times. And as I get farther out there, a lot of flips, there's going to be this little bitty epsilon, and it's a very small difference between my theoretical probability, which we know should be 1/2, and my experimental probability. Okay, because experiments, who knows what's happened during the experiment? Maybe there was friction, or maybe, who knows, maybe I put spin on the dice as I threw them, or whatever. So 1 or 2, what he's saying is 1 or 2 of your events where you throw the dice or you flip the coin or whatever, who cares if it's exactly theoretical, okay? But when you do it a lot of times, you're going to be really close to the theoretical. So if I flipped my coin 1,000 times, and now we have lovely computer generations, right, simulations that let me do this. If I flip it 1,000 times, probably my percentage of heads is going to be maybe 52% or 53%. So it's getting really close to 50%, okay, or half. And that's what his limiting theory said. It's really pretty ingenious use, I would say, for calculus for 400 years ago when they're just now developing the calculus, basically. So, pretty cool. And we use it today. It's called the law of large numbers. So, yeah, brand new, that's his thing. So this is what he is known for, FYI. So mark that in your notes or whatever. It doesn't mean that he didn't do a lot of other stuff. He did. But this is the biggie. Okay, let's talk about his brother. Yay. James and John. Fortunately, you're not going to have to keep them separate necessarily. You just need to know, I'm not going to say, did James do this or did John do this? Because I feel like there's so many of them, Daniel and Nicholas, different ones. I actually think there are 2, in the big scheme of things, there are 2 Jameses. And by the way, it's an interesting, weird thing that happened back then. People would go by different names. And so maybe it's more like their, I guess, Christian name versus their a nickname or something like that. So James, some of his writing, you'll see it Jacoby, and I don't know if that's like one of his middle names or what, but so almost always when you're reading a book, they'll say also known as Jacoby or Jacob, okay, you'll see that. And John, sometimes he'll be known as like Johann, Johann, and again, probably it's like the Swedish, I don't know, use of their name or something like that, some kind of nickname or change for it. Like your name might not be the same name if you said it in French, right? So that kind of thing. All right. So anyway, there's lots of them. So you're not going to have to keep one Bernoulli separate from the other Bernoulli, right? Necessarily. But to have an overall idea of what these guys did is what I'm after. Like you have the basics. John Bernoulli, his dates are 1667 to 1748. So he's born about 13 years after his older brother, but he lives an extra like 43 years, so a long time after his brother dies, for him to I guess, relish the sibling rivalry. Okay, so as was often the case in those days, the father normally would tell you what you're going to do with your life. Okay, right? So the first son was supposed to go into ministry. He was supposed to be a theologian. The second son was supposed to take over the family business. That was his job. That's what was expected of him. And their family business was in trade. And apparently they had a pretty lucrative family business. However, it said that John was terrible at it. Okay, and he had an apprenticeship where he was supposed to be learning the family business basically, and that he was just miserable at it, and he did a terrible job with it. So eventually he also defies his father and breaks out on his own. The reason he's able to do this is because he says he's going to study medicine. Okay, and I guess if you're not going to take over the family business, maybe it's okay if it means there's going to be a doctor in the family, you know. So that's an honorable study, I guess. So it's okay. However, while he is out there studying medicine, of course, we know his older brother has been tutoring him in math and science, right? And this becomes one of his loves. And then he finds that he can also tutor other people, and in fact, he makes a lot of money at it, being a math tutor, basically. So at some point, he says, okay, I'm not going to do it. I like these Leibniz papers. It becomes a big thing. Leibniz, his calculus, his notation, and all that. So I'm going to study that. Study math. That's what he's going to do. And he just defies his father. Okay. He becomes part of the group that's studying calculus, and at some point he becomes a professor of math. At this school is Groningen, Groningen, and it's in the Netherlands, which is like separate from Switzerland, which is where he's from, right? 1695 is whenever he becomes a professor of math. Okay. So his older brother has been a professor of math in Switzerland. He does a similar thing in the Netherlands. And then when his brother dies in 1705, which is 10-ish years later, he actually, John is offered his brother's seat as the department chair, basically, back in Basel. So he takes over his brother's seat. Which is something that wouldn't happen in these days, right? It's probably some form of nepotism or something in today's modern society. But back then, he did that. And he stayed in that position till he dies. Okay, so both brothers take this position, University of Basel, and they stay there till their death. So it's kind of nice to be back home, I guess. Okay. He is a part of this group that is sending out challenging math problems. And like I said, he found that he could make money tutoring. And so one of the people that pays him to tutor him in math is the Marquis de l'Hôpital, which, as I said earlier, I'm sure you have probably heard the name L'Hôpital, right? There's L'Hôpital's rule, and you probably learned it some point in Calculus 1 or Calculus 2, right? And basically what it says is, what? If I'm taking a derivative, or the limit of something, and it ends up being a 0 divided by a 0, instead of saying, that's inconclusive, I can't do anything with it, L'Hôpital's rule actually tells me how to handle that, right? Okay, so that's this guy, and he's being tutored by John Bernoulli. It's kind of cool. The not cool part is that the Marquis pays him even after he goes back to Basel, and they're writing letters back and forth where basically the Marquis says, what I want is when you do any new math, when you come up with any new math, you share it with me and only me. Okay? Write it to me in a letter, and I'll keep up with it, and I'll pay you to do this. Okay, that's cool. So he's happy to make the money, basically, and he does this until such time as L'Hôpital puts out a book. And basically, it's all of their letters and other stuff put together into what becomes the first textbook in differential calculus. Okay, So how do you deal with this situation when you're taking a derivative? How do you deal with that situation when you're looking at a limit? Those kinds of things. And they've talked back and forth basically for years in these letters, and the Marquis de L'Hôpital, aka L'Hôpital, has put all this together, and he's compiled it and put it into one location. And his point is, I paid you for your knowledge. You said I could do with it what I wanted. So I did. I put it in a book, okay? And he publishes it, and actually the book is very, very, very popular because it takes Leibniz's theory that was kind of up here, and the book says, okay, this is how you deal with that. Because remember, this was John Bernoulli kind of tutoring L'Hôpital, so he broke it down really easy for him. So L'Hôpital is able to put it into almost layman's terms so that other people can learn this calculus, and so it makes it more accessible to other people, the calculus is. So it's very popular. In the foreword, oh, the arrogance, it's so amazing. L'Hôpital thanks John Bernoulli and Leibniz for all of their assistance. Thanks them for their assistance, thanks them for the thoughts or whatever. But then he says, but anything that they gave to me, I have managed to turn it around and make it better, basically. And so I'm publishing things, and it's mine, basically. I return their works to them, expanded and duplicated. Okay. So it's not just their work. I did some stuff myself, and so it's all good. John is clearly not happy about this. He's a little bit bitter, and when the book becomes even more popular, he becomes even more mad about it. It's interesting to me that he says the same about Leibniz, because supposedly the book basically acts as if everything that's in it, it doesn't say that it's all mine, but it acts as if he came up with all this stuff, like even Leibniz's notation and stuff like that. So he just kind of throws it all out there as if it's his own stuff. So it's a little bit of a problem. In 1921, there's a manuscript that's found. So this is 300 years later, basically, right? In the library at Basel University, which is where the Bernoullis worked. And basically, it is original works from, I have a date somewhere. Nope. Thought I had a date. I want to say it was like 16, I don't have a date on it. So let's just say 1600s, showing Bernoulli had knowledge of L'Hôpital's rule first. Okay, so basically there's proof out there, and it was discovered long after all these guys had already passed away, that Bernoulli really did come up with L'Hôpital's rule on his own. We didn't change the name, though. I do have the date for this book by L'Hôpital. It's 1696. I want to say it was like, gosh, I want to say it's like 16, I can't remember the dates. I want to say it's like 89 or something like that is when the dated material for that proved that Bernoulli owned it first came out, but I can't remember. So anyway, there is proof it really was his. One other thing that happened is, so James Bernoulli is actually, in some of his writing, his Ars book that he put out, he puts out the word integral. I mentioned it earlier. And he talks a tiny bit about how when you're doing basically the inverse operation of a derivative, differential is what they were calling it, that it's an integral, and he used that word. He's apparently the first person that we know of who used that word integral. So he kind of gets a little bit of credit for terming this, or whatever you would say. But about this time, Leibniz is reaching out to John Bernoulli, and he wants to clarify and unify notation. Now remember, Leibniz has been notation, notation, notation the whole time, always. And he's actually also very collegial, right? He wants to work with people. He writes letters to people, and he tries to get them to work on stuff with him, and he's really group-minded in that. And so he says, look, as we move forward in calculus and math, it's going to be a problem if one group is using one notation and another group is using another notation in this calculus. So we really need to unify our notation and make sure that everybody's basically using the same stuff. And so he's already got the dy dx. Remember, we already know differential calculus. Leibniz already got that notation. So when we start talking about integrals, Leibniz is using a cursive S in front of the equation he wants to take an integral of. Okay? And he's like, there's got to be a better notation for this or something. And so he and John Bernoulli are actually the ones who kind of come together and they're working on it. They're also trying to get a name for this portion of calculus because derivatives already has differential calculus, derivative calculus, right? And so they're trying to name the second portion of calculus, which is all about integrals. And Leibniz wants to call it basically summation calculus, because that's what you're doing, right? The curve, sum of a curve, and area under a curve and stuff like that. So he wants to name it summation. And John Bernoulli is the one who says, no, we really need to call it calculus integrals, and kind of steals that word almost from his brother. Not steals because it's already out there in publication, but almost gives a nod to his brother. Okay, he's already kind of termed this, and so we want to name it that. So they kind of come up with a compromise that John Bernoulli will name it. Okay, it's called integrals, and that's what we use today. And Leibniz's notation will be used, but for some reason they're like, this just isn't working for us. So the saying is that basically it went from S. Oh, because by the way, John Bernoulli's notation was a giant I, like a capital I for integral, and that just wasn't working for us. So that it kind of went from an S to a scripted F, and that then they said, no, we don't like that either. We like the S for summation, for that idea of summing things up. So they kind of put those together and came up with that notation, which we recognize today, right? Okay, so Leibniz gets the notation, once again, just like he did for derivatives, but Bernoulli gets to name it. And so that's the way that kind of ends up for the two of them. And but they worked it out and they compromised, and that's kind of nice because it's much less contentious than what they had with derivatives, right, with Newton and everything. They work together. It's okay, we can work this out amongst ourselves. Yeah. Okay. Yeah, I have a note here that James first used the name integral in 1690, so kind of using stuff that James had already said. Okay. So that's the second Bernoulli. Okay. If you read your book, chapters 9, let me think about it. I think it's chapter 9, 10, and 11. I think they talk about 5 or 6 different Bernoullis, okay? So you'll see Daniel's in there, Nicholas is in there, all the different things that they did. These are the 2 that I feel like had the most impact on the math that we use now, which is the calculus. So they're the ones that we're going to talk about, and you should know them. But the other ones, not so much. They're in there. You're welcome to read and see what they have to say. No worries. Okay, those 2 Bernoullis. Everybody good? Anybody heard of de Moivre before? De Moivre's theory? Oh, de Moivre. Abraham de Moivre. We're not going to talk tons about him. There's an entire section about him. Let me see if I can spell his name. Abraham, D-E''Moivre. De Moivre. French name. I can't speak French, so de Moivre is the way that I was always told it. His dates are 1667 to 1754. Okay. So, again, this whole chapter is kind of about probability theory and how that came about. And we see this pulling together of the calculus with the probability, but he in particular is looking more towards the probability theory. He writes a book. It's called The Doctrine of Chances, and there's a huge rest of that. Doctrine of Chances. Goes on and on and on and on, but that's basically what it is. There's an alternate title for it, The Method of Calculating the Probability of Events in Play. It's a lot of stuff. 1718. That's when it was written. The coolness of this is it's written in English. Yay. This guy is French, but I believe he was a French Protestant. Yeah. French Protestant, and again, being persecuted, and his family or whatever has escaped to London in England, and so they're taking refuge there. This is all about the time of the Huguenots and stuff like that. So if you remember, there's a war going on with that. I don't know all the details on that one, but it's a lot of anti-Protestant stuff. So these people will leave their countries and go other places just so that they're not persecuted. Okay, so he's there, he's in England, and he actually is a private tutor in math. Now, he doesn't want to be a private tutor in math. He wants to be a math professor. The problem is that if you're in England and you're not an English person, like a native English person, you're unlikely to get a job at a university in England. Okay, so they're probably not going to give you that. So he's trying to make his way as best he can. We don't have a ton to say about him, except for there is lots of stuff about him. He supported himself by games of chance. That's a fancy way of saying he gambled for a living. But more than him betting, what he really got the money off from was from rich patrons, okay, so people who were royalty and stuff like that, asking him how much to bet. So they would pay him, give him quite a bit of a, oh man, this thing stopped. I hope it's still going. Give him quite a bit of a salary, so to speak, for telling them, okay, for this race, horse race or whatever, you should bet this and this and this. There it is. Good. Okay, for this event, these people playing this card game or this dice game, you know, you want to bet on that, you can bet a lot of money on that. Or, ooh, don't bet a lot of money on that because the probability is low. So he's made his living not just playing games of chance, but also with his ability to predict stuff. So that's what he's doing. He is writing in English, and there's not tons about him except for we know that he loses both his sight and his hearing as he advances in age. There's an entire theorem out there that's called de Moivre's theorem. That is about what the probability of such and such event is. Okay, so he gets his name in the mathematics history book. Kind of one of the cool things that he's known for, there's two of them. One is that he predicted the date of his death, supposedly. So there's a weird story that goes with that. Supposedly Cardano did this also, by the way. But there's a weird story that goes with this, and it goes like this. As he was losing his sight and his hearing and getting older, he kind of fell into a depression, and he started sleeping more and more and more each day, and just no will to live, basically. And that as he got up close to sleeping 20 hours a day, that he started saying, what he said was, the day that I will die is the day that I will sleep for all 24 hours. So as his time got closer and closer, that he was sleeping more and more each day, adding an hour or so a day, basically, he figured out that, okay, my death will be this day, and supposedly that's when he died. So kind of an interesting little sidebar there. He had predicted, or I don't want to say predicted, he had estimated, sorry, and this is kind of one of the cool things that he's known for in mathematics, in factorial. Okay, so a value for n factorial, and basically what he said was, at first he says there's some constant that whenever you, so n factorial is approximately equal to, whenever you put it in here, we'll have this constant going on, and it's the, square root of 2 pi n inside of this constant, and then n to the n, e to the negative n. So he didn't know that the constant was 2 pi, square root of 2 pi, basically. Okay. So he said there's some constant that whenever we do this calculation, and he's got the rest of this formula going out there, we'll have the value of n factorial. And so he did a really cool thing. He had already put this out there, he just didn't know what the square root of 2 pi part was. And he gets to talking to some of his friends, and one of his friends, his name's Sterling, actually comes up with, it's the square root of 2 pi, and comes up with that value. And so in one of his writings where he's talking about n factorial, what de Moivre does is he says, my good friend Sterling says, and gives him credit right there. Boom. And so later this becomes known as Sterling's theorem, or Sterling's formula, because he's the one who actually came up with that constant, and without the constant it's very difficult to calculate this thing, right? You don't really know what it is. So instead of grabbing for the attention, so to speak, he gives the credit to his buddy, which is appropriate because his buddy should have it. All right. Which leads me to the last person we're going to talk about in this chapter, Laplace. You ever heard of Laplace? See, we're getting to more modern people. We know some of these names, right? Okay, so Pierre Laplace, this is the last guy. He's clearly French, 1749 to 1827. And again, just make sure that as you're, I put up that thing in the course shell that was about the historical mathematicians, right? So So as you're looking at these, look for their most important things. You don't have to know every little story or whatever, right? So this guy, he's from Normandy. He's from a very poor family. From the ages of 7 to 16, he was educated by Benedictine monks. Sorry. Silly computer. There we go. So he basically got the poor man's education, if you will. He was very apparently sensitive to the fact that he got a poor man's education. He couldn't go to one of the more ritzy private schools or whatever. So poor upbringing is what I would say there. When he gets old enough, by the time he's 16, he goes to the University of Caen, maybe? C-A-E-N. And he's supposed to study theology because he was educated by Benedictine monks, right? So he's supposed to do theology, and he says, no, I don't want to do theology. He wants to do math instead of theology. The drawing of the math, who would know? So instead, he goes to Paris. Okay? That's what he's going to do. And when he goes to Paris, he actually goes, like the Benedictine monks and different ones, send him with letters of recommendation, like letters of introduction, okay, to other really famous French mathematicians. D'Alembert, D''A''L''E''M. Let me throw that out there. D''A''L''E''M. D'Alembert, however you would say that. He's got letters of introduction to this guy. Basically, they're wanting this really famous French mathematician to take him under his wings and help him out. Like, show me the ropes and make sure I don't die on the streets of starvation and stuff like that. Basically, he goes and he can't even get an audience with this guy, this famous mathematician. Can't even get an audience with him, can't get him to help him or anything. He won't even read the letters, okay? Won't even read the letters. And so Laplace has to kind of make it on his own. And so he's working away and he's trying to better himself and put out some math theory and this kind of stuff. And basically what he does is he writes a pamphlet or a book, a small thing, on the mechanics of the heavens. That's what Laplace is known for. So writes about the mechanics of the heavens. That's what he calls it. And apparently it is such a good writing about how planets revolve around the sun and or orbit around the sun, I should say, and about how the math of that works, that all of a sudden D'Alembert reaches out to him and says, oh, you need no introduction, your work speaks for itself. So basically, I wasn't willing to give you the benefit of the doubt whenever people were vouching for you, but now that I see that you're not a slouch in the math department, now I'll work with you. So this was a very impressive work, apparently. Okay, so he writes this thing about the mechanics of the heavens. He becomes a professor of math, and again, it's interesting because on his own he would have been in trouble. He would not have been able to do this, but he goes to the Paris École, E-C-O-L-E, Militaire, M-I-L-I-T-A-I-R-E, and this is 1769. And he manages to get a professorship at the Académie Royale des Sciences. Sciences. And basically, this is kind of like the French equivalency to the Royal Society, right? Okay, so this is their Academy of Royal Sciences. And he gets this position, which is